Let me present my screen. And you know, you might even want to add last night's homework. It's what I would actually call one of the special problems. So the guy holding a box against the wall shows itself on the exam almost every year. Never more than just one multiple choice question. Certainly not if I would definitely not expect it to be a free response question, but multiple choice, it turns up. So you want to note that down. I'm going to give you the solutions and describe all that to you. Just haven't made them yet. I'll do that maybe at 1 or 2 o'clock and I'll post it. But that's, I don't know what you want to call that. Block pushed against vertical wall, I guess, if you want to call it that. All right, so this one is the sled problem. Doesn't have to be a sled. Usually they present it in the context of a person pulling a sled, usually, even in your textbook, which, by the way, I will mention. I hope you use your textbook. You know, especially if you got it for $5. What a deal. It's got an awful lot of great information, images and pictures in there. It has good example problems. And even for AP students, there's a lot of students that if the teacher doesn't ask me to turn to page 365, I'm not opening it. There's a lot of students that are that way. And I want you to think, you know, again, this discussion about a lot of you are going to be in college, some of you far sooner than others. That has to be your norm, right? When you have something, sometimes the professors will say, this is where I want you to look, this is what I want you to do. Other times it's just expected that you're doing that already on your own. So my recommendation is, if you're not already doing that, consider doing that. Consider when we're in the middle of a unit saying, well, open that book up. Maybe I'll just take a peek at the forces unit. Maybe you'll be surprised. There's the inclined plane problem. There's the sled problem. There's the, they're all there. You'll see they're not just, you know, Mr. Kurtzak special problems or AP college special problems. They're in the textbook. They're in the textbook 99% of the time. The tugboat problem I gave you, in the textbook. They're all there. So I would highly encourage you to look at those, because those examples are not only provided as the problem, but the full solutions, step-by-step instructions, all the conceptual descriptions, they're all there. But, you know, it's up to you. It's up to you but I would encourage you. I would encourage you to consider that. I'm definitely not a textbook teacher. I'm not somebody that's just every day, let's open our textbook. Today we're on page 352. You know, I'm sure there's teachers out there that are that way, and that's fine. That's their thing. It's not my thing. It's definitely not my thing. I don't need a textbook. I have the textbook in my head. I don't need it. So, but I would encourage you to consider using yours if you're not. That's all. All right, let's move on. The sled problem. And I guess one other comment is about textbooks and resources. Is the Princeton reviews are pretty good. You can get a Princeton review for only $20. They're pretty darn good. Joey would probably say are helpful. Would you say? I mean, they're not like, you know, outstanding, but they're good, right? They're good. They could be better. There's some parts that could be better. Would you say, Joey? But they're pretty good.
Yeah, they're really good, actually.
Yeah, I mean, it's, especially when it comes to summarizing a unit. I don't know if they're good for learning a unit. That's what the teacher's for. But done with a unit, they are good at summarizing, right, Joey? All the main points are pointed out.
Yeah. So if you wanted to be for an exam, they're really good for that.
Yeah. For physics, all the special problems are in that book, every single one of them. So they're yellow. Princeton reviews are usually a yellow book. You can get it from Barnes and Nobles for $20 usually. Buy it online, of course. You can probably even buy it used. I mean, if you're an Amazon family, which many people are, but maybe not everyone. But if you have that option, I bet you could buy it used for like $5. I'd be willing to bet. It would be AP Physics 1, though. Make sure it says AP Physics 1. That's the course that you're in. There's multiple AP Physics courses. AP Physics 1. And you might even want to consider that for other classes you might have. AP classes, of course. All right, let's do this. The sled problem. So there's the ground. There's some sled with something in it, presumably a person, I don't know. And then there's some person that is pulling the sled. It's not always the sled. I mean, sometimes it's a sled. Actually, I'd say a lot of times it's a sled. A lot of times they show up, they literally will put an image in the test of a person with a hat on and everything pulling a sled. But maybe not. If not, then they would just boil it down to its essence. Not sure why that just vanished. Like the whole Google Meet I just had behind. Oh, you're still there. Thank goodness. It just disappeared off my screen. I'm not sure why. If this is boiled down to its essence, which they sometimes do, then it's just that. That's boiled down to its essence, meaning it's not necessary to show Sled. It's not even necessary to show the person. At its essence, there's some object. Of course, it's a box sitting on a floor. They might describe the floor. They might not. They might say it's friction. They might say it's no friction. They might say it's snow. If they say it's snow, I want you to tell you if they say it's ice or snow, then that's their way of saying, you know, the friction is so small, we're going to assume there's none. They don't always say no friction. Usually you can assume that if they make no comment, then you would assume it's no friction. Sometimes, though, again, they make the comment that an object moves on a slippery surface, or the object moves on ice, and that's their clever way of trying to see, does the student know that we're going to assume that means no friction? And you got to be able to read between the lines sometimes with them. But at its essence, this is what the question would look like. And it's being pulled, of course, at an angle. That's why I have to reference the theta, the angle. Motion is in the rightward direction. And there's a different, you know, there's a handful of questions, just like all the special problems. There's literally a small, not even a handful, like normally 2 or 3 most common questions that come from every special problem. And I always try to teach as many as I can. I know you're not going to memorize all of them. There's no way. But if you can remember most of them and you develop the skills to figure them out, then you'll do fine. So, like I said, there's a few questions they can ask, but usually when you're dealing with forces and you're dealing with angles, you always have to break it up into the components. No matter what they ask, you, I guarantee you're going to have to first start with, did you break those into the components and figure out what the X component is and the Y component? Just do it. Just know that if there's angles and there's forces, just say, I know that's step 1. Then look at the question after that, because I guarantee you can't answer any questions they might ask if you don't have that figured out. So let's do that part. Here's F. Here's Fx. Here's Fy. Here's that angle theta. That's not the angle 0, it's the angle theta. I like to say applied force. I'm just telling you that's not their style. They will say applied force. I should say they'll say it. They'll type, you know, there's no force applied to the sled. Not always, but sometimes they just say there's a force F. That's just what they call it, force F. All right, force F. They would never call the weight force F. They would never call the normal force F. But when there's something pulling on something, a lot of times they just say it, force F. Force, comma, F. Okay, force F. What would the Y component be for each of these? I'm sorry, what would the components be for each of these? What would the Y component be? What would the X component be? You can think about that. This, again, is something that I think you should be able to do within less than 10 seconds. In terms of what would the formula be for Fy and Fx in terms of F and theta? Because we've seen a lot at this point. If you're not able to do it, then maybe you come from some extra help. If you think, no, I know what you're talking about, I can do that in about 6 seconds, and say, good, you're right on where I'd want you to be. You think about it. What would those be? What would those expressions be? No numbers, just expression for Fy, expression for Fx.
Mr. Kurzak?
Yeah.
Fy is mg fg cos theta, correct?
Did you say Fy or Fx? I couldn't hear what you said in the beginning.
Fy.
Fy will go. Remember now, when you choose cos, you did.
Oh, wait.
Just remember, always think, well, what are those ratios? Cos actually goes with adjacent.
Sorry, it was sin. Sorry.
Yep, no problem. Yep. So Fy would be a sine theta thing because Fy is opposite. It's to the other side, opposite to the angle. So you know that that's going to be a sine theta, and this one's going to be the cos theta because X goes with the adjacent. That's the adjacent piece, and cosine goes with adjacent. Y, on the other hand, goes with sine, right? Sine is an opposite over hypotenuse thing, right? And then what goes in front?
mg.
Good guess, but this is not a weight vector. This is just somebody pulling with a force F. This is Fx.
Oh. Would it just be force then?
Yep, you got it. Just F. So your components are F sine theta, F cosine theta. All right, let's move on. What would a, again, I haven't even said what the questions would be yet. I will in a moment. What would a free body diagram look like for this? Just remember,
You'd
there's
have
no,
your normal force
I'm
and
sorry, I
your
just want to point
gravity
out there's
force.
no friction. I should have added that to my picture. There's no friction. Okay, go ahead, Zoe. Was it Zoe? Go ahead. Who was talking?
You'd have the normal force,
Yep.
the gravity force, and then the force of the applied force, the force of the man pulling.
Yep, you got it. Now, if there was friction, and I will tell you this problem sometimes does have friction, and it does make it significantly harder. A lot of times when they decide whether are we going to throw friction in this problem or not, changes the difficulty quite a bit. So we're starting with just no friction. I'll go over a frictional case with you later. That would be it. If there was friction, it would be to the left because the motion is to the right. Do you think Fn and Fg would actually be equally long, like we normally write? We normally write Fn some length up, Fg some length down to represent that they're equal in amount. Do you think that would still be the case?
Yes.
Anybody else? Thank you for your opinion.
No, because there's an upward force from the pulling.
Nice. Is that Ashley's voice?
Yeah.
Nice. Yep. There's an upward Fy here. And what does the total vertical forces have to add up to? It's not moving up. I didn't mean to say that. What is the total vertical upward? I might have messed up my words there. I meant to say, what is the total vertical forces up or down? Those are all vertical forces. What do they all have to add up to since it's not moving up and it's not moving down? It's moving rightwards.
The force of gravity.
What would the net y component force have to equal? If it's moving this way.
Would it have to be 0?
Yep, have to be 0. There's no addition, there's no unbalance in the upward or downward forces because it's not moving up and it's not moving down. It's moving rightward. All right, so let's think about how that would play out then. This is how I teach it conceptually. It's the only shot you have at doing well in physics, in my opinion. So what that means is that the Fn up plus the Fy component, which is right there. Oop, let me just draw it differently. Plus Fy has to be equal to what?
Gravity.
Fg.
You got it. Yep. This is really no different than the sine problem where we said the y component from the tension on one rope plus the y component of the tension on the other rope have to be equal to Fg down. Same idea. All ups have to equal all downs if the thing is not moving up nor down.
In this case, why does F of n equal less than gravity? I mean, I get it's because there's no upward motion, but like, is there a reason?
It's not, I'm just writing that conceptually yet, right now. I haven't yet tackled like how long each one will be, but we'll do that in just a moment.
No, like, why is that less long? Because if
We're gonna
the
talk about it. I'm gonna
if
talk about
it's
it.
you know
I'm going to talk about it in just a minute. Okay, so what we do is we have to think, how would we represent these things, right? We'd say Fn How would we represent this idea in an equation? Fn plus, because there's no expression for Fn, it's just Fn. Plus Fy, but is there an expression for Fy? You did it right in the beginning. What was the expression for Fy? F sine theta, right? So this is us just saying Fn plus Fy has to equal the weight, which we know is mg. So you go from something that's sensible, a picture, the idea that two upward forces have to be equal to a downward force, and then you get to something that looks a little more complex. Fn plus F sine theta equals mg. Well, that's what the statement is saying. Now, with this in mind, sometimes what they would do is ask you to solve for the normal force. That sometimes is their question. Let's tackle that. Sometimes the question, the only like a multiple choice question is, find Fn, or what is an expression for Fn? How can we use this model, Fn plus F sine theta equals mg, to find that expression? Well, we're just going to subtract this to that side, right? Minus it over to the other side. We end up with Fn equals mg minus F sine theta. That is the expression. Now we're going to try to talk about what it means, and then come back to Zoe's question. Remember that if a block is not being pulled in that same sled, for example, was just sitting on the surface like this, and there's nobody touching it, just sitting there, then we know that Fg and Fn are equal. We know that Fn would be equal to mg, right? So that means if we remove the F sine theta because there's nobody pulling, it's just sitting there, that means there is no capital F, it's 0, and there's no theta, there's nobody there. Then we would erase the F sine theta and the minus sign, and what would we be left with? Fn equals mg. It has to boil back down to the essence of what the simplest cases, which is just sitting there. Soon as somebody starts to lift, have an Fy component to that lifting effect, what would that do to the normal force? Remembering that the normal force represents how much pressure is underneath that box. Think of it as a scale. A scale reads the normal force. When you stand on a bathroom scale and look down, whatever that reading is, that is the normal force. That is the amount of pressure underneath your feet. So if you're standing on a scale and nobody's touching you, you're standing on a scale just like a box sitting on a floor, and you look down, what do you read? Your weight, mg. The normal force equals mg. But in this unusual scenario, somebody comes behind you, puts their arms around you, bear hugs you a little bit, and provides a little bit of a little upward lift, and sustains that upward lift. Not enough to actually lift you off the scale, but a little bit of an upward lift. What would happen to the scale? The scale reading goes up, the scale reading stays the same, or the scale reading goes down.
The scale reading goes down.
Scale reading goes down. On the other hand, if they came behind you and put their hands onto your shoulders and pressed down on your shoulders, what does the scale reading do?
The scale reading goes up then.
Goes up. It increases the pressure under your feet because they're pushing down on your shoulders, right? So you can't assume that Fn is equal to mg always, only in the simplest case when nothing unusual is happening. Something is just sitting there. Then Fn is equal to mg. Or somebody's pulling perfectly to the side and there's no other vertical forces other than Fg and Fn, and a full sideways horizontal pull, use it rightward, Fn is still equal to mg while it slides. Soon as you introduce a third y component, changes everything. Then the normal force will either increase or decrease depending on if the Fy is an upward lift or if the Fy is a downward push. And so it makes sense if I said to you that I weigh 200 pounds and I stand on the scale and it says 200 pounds, but you come behind me and lift upward with 10 pounds of force on my waist, we know that that's not going to make my feet come off the ground. You'd have to lift with more than 200 pounds to make my toes come off the scale. But if you were to come behind me and lift upward with 10 pounds of force, while I'm standing on the scale, what would the scale read? 200 pounds, 210 pounds, or 190 pounds? If you're lifting upward on me with 10 pounds of force, and I weigh 200 pounds, and I'm standing on a scale, it will read 190, right? It'll read my weight, mg, minus 10 pounds, minus however much you're lifting, because F sine theta is the expression for how much you're lifting. In this complex scenario, that y component is expressed as F sine theta. It is the amount of lifting force. Therefore, does it make a sense that there's a minus in between those two instead of a plus? It does. It does. Shouldn't be a plus. It should be a minus. Because the pressure under your feet will be equal to what you weigh minus some amount because they're lifting up on you. Now, with that in mind, we can return to Zoe's question. If we were to draw a free body diagram to scale, meaning each vector will be, either longer or smaller to try to represent a certain idea, then that can become more complex. Let's see. If I drew mg down and I drew F this way, how tall would I make Fn? Would I make Fn only go to the dotted line, under the dotted line, or above the dotted line?
To the dotted line.
To the dotted line. Why do you think straight to the dotted line?
Because then F with a Fy compensates for the rest.
You're totally right. Nice job. It can't be longer. It would have, in my picture, if it was like this, if it happened to be like this, and we had this amount over, right? Then the total up has to equal the total down, right? Slide this one over. Slide this one over. Has to equal that, which is equal to that, right? Makes sense. So technically, the normal force would be shorter and the gravity force would be longer. You draw something like that. If you actually had it like that on an AP exam, the score would be highly impressed because probably 1% of students would actually be able to think that through and actually get it like that. But that's what it would be. Soon as this force is removed, if we say stop pulling the sled, and all of a sudden this removes, what happens to the normal force? They stop pulling the sled and they just let it go. Now the kid is just sitting in the sled, just sitting there. What happens to that normal force vector that's pointing up? Does it get shorter? Does it stay the same? Or does it go up?
It equals back to mg.
Yep, back up to mg. Because it has to make up for the fact that that person isn't lifting anymore. So the floor is going to have to push harder to make up for it, make up for that difference. So there's always the most normal force when there's nobody touching it. Or if somebody's pushing down on something, which I haven't done that yet, but that would create a normal force that's more than Fn. More than mg. But when someone lifts up, that normal force then decreases. Okay, one other idea, one other question, which I'll try to get to you in the next minute or two, which is actually going to be one of your homework problems. It's the same question. The same exact question. No friction. No. Do I want to say no friction? Yeah, I'll say no friction. This is F. If someone says, what is the acceleration? What is the acceleration? What is an expression for the acceleration? Knowing that this is theta. We have to then know that if this thing is moving just to the right, they would say box is moving horizontally on a flat ground, then we have to focus on the x component forces because that's what causes a horizontal acceleration. If we go back to our diagram and think, wait a minute, what are our x component forces? Certainly not Fn, certainly not mg. What was the only x component force? it was actually Fx, right? It's the x component force from that rope, being if it was a rope that was pulling. So technically, this is just Fx divided by m. But what is the expression for Fx? Of course, they'd have an expression in there. Let's go back to the very first thing we wrote down, which was the expressions for Fxy. Fx would have to be cos theta or sine theta?
Cos theta.
Nice job, Jaden. F cos theta. That would be the expression, assuming that there's no friction, right? It's whatever forward force providing the motion, causing the motion, driving the acceleration, driving the force that's driving that acceleration forward, divided by the mass. Now, I want to point out, what if there's friction? And that's what's going to be your homework problem. It's going to be harder than this. Still doable. Just knowing that if there's friction, which way would the friction force? To the left, right? This thing is sliding across now something that's frictional. Everything's the same about this problem. Just now they say, but there's friction. And they ask to derive a formula for the acceleration, which is the horizontal acceleration. Assuming that it slides to the right. Your answer would have to be in terms of the amount of force, F, that's the magnitude of the pulling force, what the angle is, because the angle affects it, right? If the angle goes low, if the rope is pulling at a low angle, Fx is really long. I mean, you're concentrating that force in the horizontal direction and it should accelerate more quickly. If the angle is more sharp, like a pulling angle that's closer to like 80 degrees, then Fx gets tiny geometrically from a visual standpoint. And that means there's not as much horizontal pulling force. It might still move rightward, but it won't accelerate as quickly, right? The angle certainly matters. The angle of your force certainly matters. So theta has to be there. What else do you think would be in there? What else do you think that horizontal acceleration would depend on? How hard you pull? Check. The angle of that pull? Check. What else?
Coast?
Coast, whether it's coasting or not?
Yes. Wait.
Well, yeah, sort of. But if it's coasting, what is the surface? Frictional or non-frictional?
Oh.
Is it coasting on a frictional? What is it?
Would it be non-frictional?
No, this is a frictional problem that you guys have to do.
So it would
And
be
it's not going to be coasting. It's because you think of, usually when we say coasting, it means it's like going at a constant speed. This thing is going to accelerate. It's going to gain speed. This person is continually pulling. This isn't just a tug and then let it coast. This is you're pulling and you're going to continue pulling. And you're going to pull so hard that this thing's going to accelerate. And run with it. You're going to keep pulling in that direction, the direction of F. You are F. You are that force F. What else would matter, though? If there is friction, the coefficient of kinetic friction would matter, right? That's mu. Sorry, that's sloppy. What other thing do you think would matter in terms of how quickly it speeds up? Think of Isaac Newton's second law. He said F mattered. Check. What else did he say in terms of the acceleration? Mass. Yep. And what they would say is, and any other fundamental constants. That's their wording. That's the AP exam's wording. When they say and any other fundamental constants, I'm telling you now, they're talking about G. And instead of them just saying G, for whatever reason they say, because it's a constant, G is 9.8, it doesn't change. They don't say it. They just say, and any other fundamental constants, I'm just telling you now, that's G. That means that you would want G in that formula as well. Just remember one last thing here, because we're done, that the kinetic friction sliding, this is a sliding friction scenario. It's sliding to the right. This thing is sliding while being pulled at an angle and that amount of frictional force is mu k times the normal force. And we just talked about the normal force today, right? That was the whole basis of the discussion, which was that y component that's lifting up affected Fn. You needed to get that expression for Fn, right? We did that today. Does that come into play for the frictional force? Absolutely. Because the frictional force depends on how much pressure is underneath that object. If it's tight, then there's a lot of friction. If it's not as tight underneath the object, there's less friction. And that tightness, the pressure underneath, we call that Fn, right? So that's my hint to you, that you'd have to incorporate that all together, all those little pieces of them together. All right, I don't have anything else to say. That's my lesson for today. I am going to ask you to do that for homework. Of course, I'm going to type it up, and I will post it. I will ask you to do one other thing, because that wouldn't be enough for 3 full days. I don't know what it's going to be. I am going to quickly say that I want you to do another lab, and it wouldn't, but I don't think it would be due probably until next weekend. But you might want to start on it this weekend. It will be a pivot interactive lab. I'm just going to say that I have to teach you about springs because it references forces. When you compress a spring or you stretch a spring, it creates a certain amount of force. It causes a certain, it requires a certain amount of force to compress a spring. It requires a certain amount of force to pull the spring. And also when you compress a spring, it pushes back on you, trying to spring itself back to its original shape. Anyways, that's all in the forces unit. And the topic is called Hooke's Law. So my goal was to pick a pivot interactive lab that has the concepts of Hooke's Law and the forces generated by springs and give you a lab. So I might very well pick that out and assign that, but it wouldn't be due on Monday or Tuesday. It probably wouldn't be due until Sunday of the following week. Just keep your eye, as always, on Google Classroom. But I'll type this up and I'll post this. All right, that's it. Any questions? Sorry that I ran a little late, but I knew we had those few minutes since this is the last period of the day. I appreciate you giving me the extra 5 minutes. Yeah, anybody have any at all? And just remember, I'm going to post the solutions to last night's homework after I do them, which I'm going to do right now. Any questions at all? All right, everybody, have a great day and a great weekend. See you next week. Bye, everybody.
Have a
Bye-bye.
good weekend.
You too. Thanks, bud. Bye.
Thank you. Bye-bye.